Hi guys, this is Paul again here with Tweaktown. We're at Storage Vision's 2014 in the booth. Right now with us we have Riccardo Badalone. He is the CEO and co-founder of Diablo. For those not in the know, SSDs, of course we know that flash is changing the landscape of the data center. First we started with 2.5-inch SSDs and 3.5-inch SSDs that plug into SATA ports, RAID controllers, and HBAs. In search of more speed, there began to become a development of an ecosystem of PCIe SSDs, because what happens is the closer you get the SSD to the CPU, the better your performance gets. Now, the PCIe SSDs have become pretty mainstream. Diablo has emerged with a technology that allows us to use an even faster bus than PCIe to provide even more performance and numerous other advantages. So Riccardo, if you could just give us a few words and kind of explain to our viewers exactly what this does.
So thank you for having me.
Yes.
Appreciate the opportunity. So the concept that we developed is called memory channel storage.
Okay.
And as you stated, the idea is to use the memory subsystem of the processor to actually connect the flash.
So you're going to plug it into a DDR3 slot.
Yep. So the final product looks like this. The form factor is identical to a standard memory module, same width, same height, and it physically just plugs into the memory channel. There's no cables or anything that's needed. From a thermal power cooling perspective, it fits into the power envelope of a memory module, and typically whatever the system integrator has done to get the power to the memory and the heat out of the memory subsystem, we should be able to just handle that infrastructure. So there's plug and play from that perspective. The benefit of using the memory subsystem is that, like the memory itself today on a processor, it's very highly parallelized, which means that there are multiple channels and there are multiple ranks within each channel, and there are two per two processor system that are shared, which is called a NUMA configuration, a non-uniform memory architecture. So what it means is that this architecture is all about parallelism, as opposed to PCI Express, which you tend to get one big pipe and a lot behind that one big pipe. We tend to build a modular solution where the approach is to spread the NAND or spread the flash across multiple channels, which gives you very low access times and a lot of throughput and parallelism.
So a lot of times when customers deploy multiple PCIe SSDs into servers, you lose a little bit of performance because the PCIe bus has to start switching and handling that bandwidth, and there becomes some bus contention. So when you add multiple drives like this into DIMM slots, how does that affect it? Do you lose anything in the scaling?
So no, the scaling is perfectly linear. Now, to be fair, the reason that the PCIe interface doesn't scale perfectly linearly, it does actually, but it depends on the circumstance.
Absolutely.
And what I mean by that is the way it works in the I/O space is that the data is DMA'd back and forth between the memory subsystem and the actual flash subsystem. Because a read and a write are really just that. You're taking the data out of the NAND and putting it into a page in DRAM, or the other way around.
Correct.
So in our case, the data never leaves the memory subsystem. And so when you're reading a page or several pages out of RAM, they can be concurrently written into several devices in parallel, and that's where the parallelism comes in. It's the same thing for reads. Mm-hmm. If the data is spread out over multiple devices, they can be concurrently read and then written back into the page, all within the memory controller itself. It never leaves the memory subsystem. So our actual flow control protocol is also implemented in the memory subsystem. And so the communication to the device is done just like communication to memory.
And latency is going to be spectacular.
Exactly. It's lightning fast. So as soon as the data is ready for you to copy into a page, our driver knows about it and can instantly move it into a page and make it accessible. In the case of the I/O space, what you're doing is you're essentially coordinating with devices that are they become masters, and they have to move the data out of memory into their own space, or the other way around. In our case, as soon as the driver is ready to do work, it can do work either from a protocol perspective or from a data transfer perspective. So it's a very different approach, and it has a lot of scaling advantages for sure.
Absolutely, and another big advantage of this is going to be using this type of model as in-memory compute, because you can pack a lot of density with NAND, especially as NAND continues to shrink. Yep. What's the max density of NAND that you can get on this device here?
So right now we're at 400 gigabyte. That's a provisioned DIMM, so it's a half a terabyte. That's provisioned at 28% to 400 usable capacity. And of course you can play games with that, but the standard nominal over provisioning and all of the performance data that we generate and publish with SanDisk are all centered around 28% over provision. It's a 19 nanometer MLC solution, which is what I would consider from an enterprise production perspective state of the art.
Absolutely.
And so again, we're talking about extremely high levels of performance with a very low cost NAND subsystem. So the scalability, the economics are all very attractive, and I think it all comes down to using the memory subsystem and the scalability it provides.
Absolutely, and you can use this in two different types of use cases. You can either use it as in-memory compute, which you're not going to find a DRAM stick out there that is going to have 400 gigabytes of space. So you gain in density there when you're using it for in-memory compute, but you can also address this, if you choose, as a block device, correct?
Yeah, absolutely. And
so it appears as a drive.
We're seeing, exactly, and actually we're seeing both. And even in the case where people are using it to extend memory, it's still being done through the block system of the operating system, because it's so fast. A lot of the hooks that are built into the operating system to memory map I/O, we can take advantage of them. So for example, if you had an in-memory database that you were looking to persist and you dirty a page and you want to actually write that page instantly, we can handle that almost at the line rate that the application can basically generate the dirty pages. And so what you see is that you can use it as a traditional storage that is backing the memory. But because the latency and throughput are so fast and so high, you can go through the traditional storage stack and still use it to persist or extend memory.
So yeah, so you're still getting big benefits there. And of course, a big problem with DRAM is volatility. If you lose power, you have to, any kind of in-memory compute that you do has to be checkpointed and backed up periodically. If you lose power, you lose data. These are tantalum capacitors, correct?
So I'm not sure if they're tantalum capacitors, but they're not super caps or any kind of weird. I think they are ceramic capacitor, that kind of capacitor.
So
they will be able to handle 85 degrees or 95 degrees. They won't degrade over time. They're designed to last for the lifetime of the product.
And that will protect the data in memory to where you can use this device and really without any fear of power loss, correct?
Yes. Yes, and actually there's full end-to-end protection designed into the MCS protocol, which means that if the data for any reason is corrupted in the process of writing it in to the devices, we can detect that and our driver can retry it or replay the commands. The same thing when the data is coming back from the NAND, every point in the data path is data protected, leading up to the software that hands it back to the application. So it can be used as a true enterprise device with full end-to-end protection. And the value of these onboard capacitors and the PFEL circuitry that's on here is that that's what gives us the incredibly low latency. The data is copied from a page into our physical chipset, and we can say that the data is written, even though it hasn't made it to the NAND. And that's what we call early commit or super early commit. It's all based on the fact that once our driver, the ASIC, tells us, okay, it's done, I got it, we can go tell the application, move on, consider it done. And then in the background, the data is shuffled off to the NAND.
Absolutely, and any kind of power interruption, it's going to still handle that and flush it down to the NAND. That's excellent. I know you guys have working, of course we're holding one, working silicon here, and these devices are being made in conjunction with SanDisk. They're using the NAND and the controllers that interface. There are two SSD controllers that interface with your controller in the MCS subsystem. Do you have any idea of when these will become general, when we're going to see general availability? I know that qual cycles can be a bit of a guess, but what would you, kind of the time frame we're looking for mass production of these?
So obviously I can't give specific dates, but what I can tell you is the product is mature. The ecosystem is mature. All the operating system drivers, Linux, Windows, VMware are ready.
Excellent.
And we're working with SanDisk and integration partners right now to roll this technology out. And so it's right around the corner.
Yeah.
I can't give specific dates, but it's definitely mature and it's solid and it's performing extremely well. And so we can expect some announcements in the near future.
And I think a big thing with a radical departure from today's typical 2.5 inch or PCIe SSD architectures, a radical departure like this can actually enable maybe even a sea change a bit in the data center, because everybody's looking for density, of course. We're seeing more blade servers. This thing's practically made for blade servers. I mean.
No, absolutely. And actually, it was an interesting use case that we spoke to a large data center operator about, actually several data center operators about. Unlike this concept of a really large device, like a big 4, 5, 10 terabyte card that goes into the system, if you think about blades and scale, in an IT infrastructure environment where you have tens of thousands of users that are leveraging infrastructure, right now DRAM is being used predominantly to accelerate I/O. You think there's software out there today that is accelerating VDI, for example.
Absolutely.
Where people have their storage architecture, they need some type of SAN or NAS type storage infrastructure. They've made the investments, and they're stuffing more and more DRAM into the system and using it honestly completely for caching.
Yep.
There's no application data, like full rate DRAM based application data being used at all for that. The DRAM is being used for I/O. Well, what's interesting about this is that you can literally replace an 8 or 16 gigabyte DIMM with a 2 or 400 gigabyte DIMM, expand the size of that
Yeah,
cache,
it's a ridiculous jump.
lower cost, lower power, and get a significant performance boost. So the economics really work, and that's a case where you're replacing DRAM, which is not really being used as an application space scratch pad, right?
Yeah.
It's being used as an I/O cache, and you're replacing it with a much more economical, more dense system that will perform just as well.
That's excellent. And I'm sure times are pretty exciting for you guys, especially as you near the opening stages of general availability.
The big thing for us now has been, there are obvious use cases where the throughput and write latency are so disruptively fast, like in high frequency trading.
People are going to have to figure out how to use it.
People have, we've done a lot of PR around that. Well, the part that I'm the most excited about is now taking this into database applications, taking this into virtualized environments that are no longer just considered niche, but more mainstream,
Absolutely.
large scale. And when you think about the different form factors that are out there, there's only one that really gives you the ability to have a reasonable amount of density, but very high performance. Typically you can get the modularity in a 2.5 inch drive, but you won't get that leap in performance, or you get a big card that has big performance. Here, the resolution coupled with the performance is a very interesting combination.
All right, it sounds good. Thanks, we appreciate your time. Thanks for
My
stopping by
pleasure.
the booth. Thank you.